Hello, this is the next video in a playlist that I'm calling correlation, and we're going to look at multiple correlation. Now, multiple correlation, denoted by R, Y, X, is the zero order correlation between Y and the predicted values using these P predictor variables. And we're going to develop two formulas for this, and both are used equally often, I guess. Y is equal to this equation, this linear equation, plus some error. Now we're going to assume that the x's are centered. That means we're going to subtract off the mean from each component. Now let's find the equation for beta, the vector beta. And we're going to look at its mean squared error, and the mean of epsilon squared is equal to the variance of epsilon plus the mean quantity squared. Now, sometimes I always have to think about it. If I subtract that over, then the variance of epsilon is equal to the expected value of epsilon squared minus the mean squared. I mean, that's the formula that I remember, and then you kind of transform it to this. Now, we put in what we know about the error term, y minus the beta x, and put it in here. Now, we take it, the variance of y is sigma yy, so I just denote it by the variance. Then the variance of this, so it's going to be plus, and then the beta transpose, then it gets transposed out back, and it's the variance of x, which we'll denote by the covariance matrix sigma xx. So the little vector signs mean it's the covariance of these vectors. So this is a P by P matrix. And then we look at the covariance between these two. So it's going to be 2 times. Now, if we take the covariance between y and beta x, the beta gets transformed out back, which is this piece. Then it's the variance of y and x, which is this. But very importantly, you have to think about dimensions. Okay? So this is a scalar. The transpose makes this a 1 by p. This is p by p, and this is p by 1. Now here, it's the covariances between y and x. So y is one variable, and x contains p variables. So this matrix ends up being a 1 by p vector of covariances. So it's 1 by p, and this beta vector is p by 1. So the dimensions do work. And here the expected value of y and the expected value of this, since x is centered at 0, so we just get this. Now let's think about this as a function of beta, so we can minimize it. So we're going to take partial derivatives of q with respect to beta, the beta vector. This is constant, there's nothing here. Now I have a video called Derivatives of Quadratic Forms that you can reference for this partial derivative. It ends up being 2 beta transpose sigma xx, whatever this covariance matrix or matrix here is. The derivatives of beta is just what's out front, set it to 0, divide by 2, add that to the other side, take the right inverse of x, and we get this. Now notice this is transpose, so that makes that a 1 by p, and it doesn't make sense over here. So y and the vector x, so it's 1 by p. So this is a 1 by p row vector, and this is a p by p matrix. So the dimensions are the same. If you want a notation for just beta, then we'd have to take the transpose of both sides. Anyway, but since in our equation we look for beta transpose, we're just going to leave it as that. So the first definition, and by definition, this is the multiple correlation, is the correlation between y and the predicted values using the x's, which is this, right? Correlation is covariance divided by the product of the standard deviation. This is the definition. So now let's put in for what we just learned about what beta is. So this goes from here. So the y's are the same. The beta we put here, right? And then we have x, variance of y, and then beta goes here, and then x. So nothing new yet. Now let's take the covariance. So the covariance between y and this. So since it's the second component, this gets transposed out back. So that's what this piece is. So here, we take the transpose. You could have the transpose of this, but also since the covariance matrix is symmetric, this is going to be the same as sigma xy. Where here this is yx. So this is a p by 1 matrix. This gets transposed, it's symmetric. And then we're left with the covariance of y and x. Well, that's this piece. So here, the variance of y, which is this. And then here, the variance of this. So this gets, and I think I have a video on random vectors and matrices and taking the expected value and the variances for a background review. So this piece is pulled out front. So that's literally just this. And then it gets transposed out back. So that's the transpose of this and that. And then we're left with the variance of x, which is this. Now notice that this cancels and becomes the identity. And then we have the same piece divided by the square root of the same. So that one of those some of that cancels with here, leaving the square root of it up here. So then we're left with this. And actually this is the formula that I wanted to show you for multiple correlation. And so multiple correlation is in terms of variance and covariance matrices. And you might say vector, because this is a vector, that's a scalar, this is a matrix. So this is one of the formulas. Now the second formula, I want to cover some background first. Let's let D be a diagonal matrices of these standard deviations, of the first variable, the pth variable. And the inverse of a diagonal matrix is just 1 over the diagonal entries, so we get this relationship. Now, as a reminder, the variance of x is the covariance matrix, p by p. Now, so correlation is covariance divided by the product of the standard deviations. So if you take this multiplication, right, we're ended up dividing these different standard deviations by the respective covariances, this ends up being what's called a correlation matrix. Now, depending upon what field you're in, whether it's more behavioral sciences or mathematical, you use different notation for this correlation matrix. Some use R, but I didn't want to confuse that with the notation of the multiple correlation coefficient. And so this is it. Oh, and look at this. I use a rho, and that should be an R. Matter of fact, I'm going to change it live. So, to develop the second equation, this is from definition 1. And what we're going to do is we're going to put the identity matrix here and here. That's what we do here. And then we're going to split this into 2 pieces, take the square root of each and put it under these vectors, right? And when you're dividing by a constant, it's like it can go into each component, but we're going to write it like this. Then this right here, remember this is a vector, and this goes under each of the covariances, and then we're dividing by another little piece of the standard deviation. So this ends up being correlations, a vector of correlations. Same way with here, the D inverse and this becomes correlations. Now notice the notation, this is y and x, so this is a row vector and this is a column vector. Now let's take the D into this. So if we look at this, if we take the inverse of D inverse, we get D, that's what this one is, and then that's the inverse, and then that, so if we take this D in here, we just get D back and it ends up being this. So this is this piece right here. But this is the correlation. It's the inverse of the correlation matrix. And this is the second formula that I wanted to point out. Now, this correlation matrix, some people use different notation, a different variable name for that, but ultimately they're 100% equivalent. So this is the second formula. So the correlation, and that should be R. Well, let's do it this way. Let's just put a little make that an R. So this one is in terms of correlations. So everything here is in terms of correlations. And one other note is if we square the multiple correlation, we get the coefficient of discrimination. So that's another property. Now, one of the reasons I'm doing this playlist of correlations is I'm writing a paper on sample size in multiple regression, which deals with this multiple correlation coefficient. Anyway, it's pretty exciting. I hope it gets accepted. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.